Hey guys, welcome back to my channel, Digital Srini on YouTube. In this video, I plan on going back to the basics a little bit, meaning let's go ahead and compare how feature engineering plus classifier, that classifier can be gradient boosting or random forest or support vector machine, it doesn't matter, extracting features plus some sort of a classifier versus deep learning approach. Since I'm talking about semantic segmentation, let's stick with unit type of architecture. So the goal is to compare these two, and let's actually put together a unit from scratch, or train a unit from scratch, and also using pre-trained weights, for example VGG16 or some weights. Let's go ahead and load that and compare all these results. And why? Because you may have seen a graph like this or a plot like this where on the x-axis you have the amount of training data, and on the y-axis the performance of that specific approach. So as you can see, with very limited training data, maybe the classical approaches are much better than deep learning approaches. In fact, I disagree with the separation between these two. In fact, based on my experience, I see classical learning to be slightly even more better compared to deep learning. Again, it depends on the application. But the whole point here is you get better performance. You may get better performance just following your classical machine learning approaches compared to deep learning if you do not have a lot of data. But if you do have a lot of training data, then deep learning kicks ass, as you can see. That is the approach you should be taking. So in other words, if you focus on semantic segmentation, if you just have a few images, and if the problem is simple, if it's a simple problem, if it's just, you have a bunch of nuclei, or you have like two different things, one background and one some sort of a foreground, then maybe OTSU is more than enough for you. Just put auto thresholding using OTSU, and then it tells you exactly where to threshold, and you're done with your segmentation. Very few images are like that. Very few challenges are like that. You may have a bit more complicated. You have like different regions and you would like to segment them. Then traditional segmentation actually does an amazing job. And I have done this for at least 5 years on tens, if not hundreds of data sets. So traditional machine learning, feature engineering, or extracting features, plus random forest or gradient boosting, you pick one. Either of those actually work very well, gives you excellent results. Now, if you have even more complicated, like the mitochondria dataset that I typically use against a very busy background, those tend to get a bit challenging for traditional approaches. That's when I try to get a lot more data and jump into deep learning. So with that background, let's go ahead and jump into the code and then just do exactly the same. Stick with our plan, feature engineering. Again, it sounds fancy, but it's just a bunch of digital filters. We are getting features, and then let's use light GBM. I like that library. It's faster. It does a great job. And then deep learning. So let's jump in. Okay, so here I'm going to share all of these files with you, and I have 4 or 5 of these to show these different examples. But here, just to show you the input data that I'm trying to work with, the training data that I'm trying to work with here, let me open that in image J so you can clearly see exactly what we're working with. Yeah, these are the two. So on the left-hand side, I'm working with only a single training image. This is a large image. This is 768 by 768, a single image. And this works for me in this case because it captures all the classes I'm interested in. I'm interested in segmenting the outside dark area and also the inside dark area, which is like my one class. And I'm interested in segmenting the bright regions, these pixels that are in gray region, and the clay, which is the textured region right there, as you can see. I have labeled it. I have labeled this image. I took very special care in defining the edges and getting these regions labeled and everything. So I have labeled every pixel. What does that mean, in case you don't know what I'm talking about? Meaning I assigned a pixel value of, for example, 0 for the background and a pixel value of 1, 2, and 3. How did I do that? You probably know this, but for those of you who don't know how to label your images, In my case, I use Appear. If I can just jump on back onto my page right there. So I use, just go to www.apeer.com. So here there are like these machine learning tools, and you can go ahead and annotate. In fact, if you don't want to write your own code, you can just click the train button here, segment and all that. So I just went to annotate. I added my data sets, and I opened my image, and I painted, like I defined 3 classes. I'm interested in 4 classes, which is also the background, right? I mean, this region, the dark regions, and plus 3 of these. If I don't label anything when I download the labels, it's going to assign that a value of 0, the pixel value, which means I'm not going to label all the black regions around here, all the black pixels, and only label these 3 classes. So that's exactly what I did. I added a class. I said, okay, my chords is in red. Use the paintbrush tool or one of those tools and just brush everything. I usually do this. And then when it comes to edges, I just go ahead and be a bit more careful. Okay, so when you do that, okay, now you defined everything, and you go ahead and export this, export it as a binary mask, select the 3 classes that we just defined, download it, and when you do that, you can just go ahead and, I mean, in this case, I haven't labeled everything. Make sure you label every pixel, because for deep learning, you need every pixel to be labeled. For traditional machine learning, you can get away by not doing that. At least the way I'm approaching the deep learning, you need every pixel to be labeled. Okay, so once you do that, then you end up with an image. If you label every pixel, you end up with an image that looks like this, where every pixel is labeled, and you can see when I move my mouse, you can see the values of 0, 1, 2, 3, and so on. And in fact, I can even open my histogram right there, so you can see list. I have my pixel values of 0, 1, 2, and 3, and these many pixels. That's it. I have nothing else. Everything else is 0. That's why if you open this image in Windows Viewer, it looks dark, because Windows is trying to show you 0 to 255, but you only have values 0, 1, 2, 3, or 4, right? Okay, enough lecture on the very basics, but again, I'm not sure what your background level is, so it makes sense for me to cover some of these basics rather than not cover. Okay, with that information, so what do we have right now? We have an image that's called, let me scroll down, this, which is my actual image, and then corresponding mask, meaning at every pixel, it's either 0, 1, 2, or 3, right? So that's our pixel values. So based on that, let's go ahead and define our traditional machine learning approach, which means I have to take my image, extract features, and use those features as input to my classifier. I'm going to use in this case, I'm going to use LightGBM. Again, I covered what these are in my previous videos, so go ahead and look, search for these terms like traditional machine learning or random forest or LightGBM or XGBoost, and get educated more on these topics. So the goal of this video is to compare and not to talk about each of these in detail. Let us load the required libraries. Again, none of these should be pretty new to you. Maybe TIFF file. TIFF file lets us handle TIFF files. You can use scikit-image if you want, because scikit-image uses TIFF file in the backend anyway. Okay, so now that I have this, let's define what features to extract. What do we mean by features? When it comes to images, features are nothing but the response to digital filters. So if I have an edge detection filter, then the output image is a feature which shows edges. If you have a texture detecting filter like Gabor or something, you're capturing how how the texture looks like. So filters are nothing, the features are nothing but digital filters. So first of all, let's go ahead and collect all of our features. Feature number 1 is the pixel value itself is a feature, right? Pixel value of the input image itself, because the brighter pixels correspond to one class, the darker pixel correspond to a different class. So I'm going to capture my original image as a feature. Okay, so that's my column number 1. And then I'm going to apply to my input image a Canny edge detection filter. Again, if you don't know what this is, you should be. Learn about all the digital filters. Okay, so this is a Canny edge, and then I'm applying a few of the other filters. For example, Roberts, Sobel, Shar, and Pruitt, all of these are some sort of a edge detection filter. So I'm just adding edge detection filters here. That's it. And then I'm adding a couple of Gaussian filters. Gaussian filters can be very, very useful in extracting features. Let's see, I think with LGBM, it also prints out the feature ranking. So it tells us which features worked well, which features did not work well. And I expect Gaussian to be one of the top 2 or 3. Okay, so Gaussian filters with a couple of different sigma equals to 3, sigma equals to 7. And I also added a median filter, that again, one other filter. It makes sense for you to throw the kitchen sink at this. Just generate 60, 70, 80 filtered images, and then supply that as input. You would increase your accuracy even more than what I'm going to show you here. Okay, so let's run this function. What that function does is, obviously, it returns a pandas data frame with all the features in it. Okay, so that's what that function does. Now let's start reading our images. So I'm using my TIFF file library to read my input image. It should be 768 by 768. It's a grayscale. And let's also read the mask. Mask is also 768, of course, by 768. Let's go ahead and have a quick look at the image in case. Let me expand that. Okay, so that's the image we are working with. And let's also print the mask. That's the mask we are working with. Okay, now that we have our image, let's go ahead and call the function for feature extraction, because what does this function take as input? An image, right? And then it does all of these, apply all of these filters. So let's go ahead and call that function. This may take a few seconds, but it should be pretty fast. We only have one single image. Now, if you look at the data frame here, let me open it. It may take a while. It's a large data set. No, that's not that bad. So you can see how we have, sorry for that. Let me go ahead and open. You see there is a median with sigma equals to 3, or a kernel equals to 3, Gaussian with sigma equals to 7, Gaussian with sigma equals to 3, Shar, Pruitt, Sobel, Roberts, Canny, edge, and our original image pixel values. So pixel value equals to 0 means we are in the dark area. So if I go back down, you will see obviously some real numbers here. Okay, so, and these are all the features. Okay, now what? So let us go ahead and read the mask and reshape the mask, because we need to add the labels next to each pixel, right? So let's go ahead and reshape it and add that to our labels column. And if I open my data frame right now, let's go ahead and do that. You should see my labels column here. So as I scroll down, you'll see that, okay, the label here is 2, and then you'll see all the labels corresponding to every pixel. This is semantic segmentation. Of course, every pixel is classified. Okay, now, I mean, we opened the data frame, so no point in looking at that. So now let's define our X and Y values for our traditional machine learning training. My Y is basically the labels column, the values of my labels column, which should be 0, 1, 2, or 3. In our case, and my X is every column, all the features except for the labels, right? So let's go ahead and define that, and as usual, let's go ahead and split our data into training and testing. I'm leaving 40% for testing, only 60% for training, which is fine. I mean, in fact, we don't have a lot of training data, but still, even with 60% training size, hopefully we'll get some decent result. Now for classifier, let's use the LGBM. Again, this is where you can use XGBoost or random forest or support vector machines, and you can try all of these different ones and see which one works great for you. So let's go ahead and import the LGBM right there, and you can install the library using pip install. And let's define our training right there on xtrain, and label equals to ytrain. And let's define the parameters that we want to use for LGBM. Again, I covered all of these in one of my previous videos, so I am going a bit fast. And now we are all ready to train the model, and here is how you train it. Model equals to lgb.train, and I have already done that, so we don't waste time right now. And I have saved the model to my local drive. In fact, if I open that, you can see I have done that with LGB deep learning unit, and also with my VGG19 as the backbone with ImageNet weights and all that. So we are going to compare these in a few minutes. So I have saved it, and let's go down to model.predict. Well, we don't have a model, so I forgot pickle model equals to pickle.open. So let's go ahead and do that. pickle.load, open file name, RB. Yeah, so now we should have our model. When I do that, file name is not defined. There you go. Let's do that. And let's load our model. Okay, so now we have the model that I trained using these settings. And now, first of all, let's go ahead and perform model.predict, and then go ahead and convert that. By the way, when you do that, your model prediction LGB is almost, this is a multi-class, right? So you get like 4 right there. This is a unique thing with LGB and not with LGBM and not with random forest. In random forest, your output would have only one channel, and that channel is like argmax, already has like integer encoded values for your classes 0, 1, 2, or 3. In LGBM, this is basically, this is almost like doing multi-class in UNet, right? So when you use categorical cross entropy. Anyway, so we need to take argmax right there to convert that into a integer encoded. So there you go. Now we have integer encoded, and let's go ahead and print the accuracy. So what type of accuracy do we get? So that's not bad, 97%. But we know that with semantic segmentation, accuracy is not what we care about. What we care about is intersection over union. So let's print some of these. Again, I don't want to go through line by line. You can read the code yourself. And what I have done here is, instead of overall accuracy, I'm only looking at class 2 accuracy. Why? Because class 2 is the most difficult class to segment in my image right here. So if I go ahead and open this image just to show you, yeah, right there, class 2 is this area right there, class 2. You know, this texture looking region, because the average grayscale of that matches the grayscale of this other gray region. So if the model does great on that class, then it's good. So that's why I'm putting special focus on class 2. So 72% is not bad. That means we got even more accuracy on other classes. Okay, so now let's go down and print out the feature importances. Again, I do this out of curiosity all the time whenever I do random forest or light GBM, because I want to know which one actually worked the best. So based on the feature importance, Gaussian, like I mentioned earlier, Gaussians are always great as feature extractors. So Gaussian with sigma 3, Gaussian with sigma 7, median, fruit, the original image pixel value obviously is also important. And here is how the importance is ranged actually. Okay, that's just out of curiosity. It has nothing to do with what we plan on doing. So now let's go ahead and apply the trained model to segment multiple files. So what I've done is, I think I have that open here. Yeah, so I have 50 different slices. This is a 3D data set, and I'm applying one 2D at a time. So I have 50 images. So I am segmenting all of these, and then I save them. And for each of those 50 images, I have ground truth. Again, meticulously labeling it yourself manually, okay? But either way, I have my ground truth right there. So this is my ground truth, and I'm segmenting it, and I'm storing those images and printing out some, and basically saving it as LGBM segmented.tiff. So if I go back and again, data, and here it is, LGBM segmented.tiff. Of course, I also have VGG19 UNet, XGBoost, and also deep learning segmented outputs that we'll compare in a minute. But I just want to make sure you see exactly what the process was here. Okay, and then I print out some of the metrics, which we'll see in a minute. So I'm skipping this part. You can go ahead and do that on your own time, and you can experiment this. I'm just leaving this for the sake of completeness. Now let's skip. I wanted to show you some random segmented images, but of course that requires me to load the data set and all that stuff. I don't want to waste your time going through that. Let's switch to the next step. So hopefully with this you understood exactly how the traditional machine learning segmentation process works. I really encourage you to watch my previous videos if you really are curious in this step itself. But the focus is in comparing these. So let's move on to our next step. Again, I have used this approach many times. So let's clean this up. Let's create a clean slate here. Again, I'll go through the code, but I'll put more emphasis on the last file here where we compare the results. Okay, so this is a traditional unit model for multi-class. Again, I explained this in the previous video. So it's basically a convolution block, convolution block, convolution, 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 all the way going down to a bottleneck, and then expansive path, or the decoder path if you want to call it. And this is as basic as it gets. Now let's use this to train our single image. So for that, I have this file right here. So again, I explained in the past how we can use Patchify to extract 256 by 256 or whatever smaller size patches for your deep learning, because you cannot load a whole bunch of large images. Of course, in this case, we only have one image, but just for the fun of it, I divided my image into patches of 128 by 128 with a step size of 128. And then obviously I do the same even with my masks, and I use those as input. And of course, of those, I divided how much? About 10% into test size and 90% into train size, because I want to train this deep learning a bit more with more data. Remember, for our traditional, we took 40% for 40% for training, for testing, and 60% for training. Okay, but in this case, 90% for training. But it doesn't matter. Well, we'll see if it matters in terms of when we compare the accuracy. But keep that in mind. And I just defined my unit model. I got this model that we just looked at with number of classes equals to 4 in our case, and image height and width are 128 and 128. Then I compiled it using Adam categorical cross entropy, because these are categorical, and at some point I probably converted my my masks into categorical. It is very important, obviously. Yeah, right here. This is a multi-class semantic segmentation, so you have to do that. And when you convert that into categorical, now you can go ahead and use categorical cross entropy. If not, you can actually use sparse cross entropy, but I don't like to do that. This is the way I usually work with you know, categorical cross entropy is what I typically work with. That's why I'm using that. And metrics, we are tracking accuracy. You can track intersection over union if you want. And I trained this for 200 epochs, this traditional one and also the other pre-trained one. So I have 200 epochs right there. And once it's done, I save the model as DL unit HDF5. That's exactly what we have. If I go back and save models, this is the one that I have. Okay, so this is the other model that we need to now compare against LGB. And finally, that's it. I think everything else is pretty self-explanatory. Then what I did was I took that model and I segmented my 50 image TIFF stack and saved the result. So later on, we are going to just work with the results and just see how the intersection over union and others will compare. This part of the code will be almost similar to what I have done before, like calculating intersection over union and all that. So that's the story with this file. Finally, the next one. For those of you who think I'm doing this too fast, you're probably thinking that because you haven't watched any of my previous videos on this semantic segmentation or using UNet or using traditional approaches. I definitely recommend you to go back and watch those. I really don't want to make this video any longer than it needs to be. I hope you understand that. Okay, so for pre-trained weights, again, you can put together your own model, but in this case, I'm going to load segmentation models library. Again, I talked about this extensively in the past, so go ahead and load the segmentation models library. And also, I'm using Patchify. So the approach is going to be identical to what I just showed you with my own unit, except it differs right here. So I'm using Adam Optimizer, and from I'm using focal loss here, and from the metrics I'm using IOU score and F score, both of these. And here I'm putting together a VGG19 encoder with pre-trained weights. So VGG19 right there. Get the pre-processing step, obviously. You need to pre-process your data exactly the way that they pre-processed in VGG19. That's what that means. And I have my X-train and X-test, and here is where I'm defining my model. So the backbone is going to be VGG19 with encoder weights equals to ImageNet weights. and I compile, I train, and same number of epochs, like 200 epochs. I also tried 50 epochs, but let's keep it consistent. And bottom part will be identical to what we just saw before. Okay, so this is how I trained these three different models, and now let's go ahead and compare the results, the moment of truth. So for this, let us run our libraries right there. We don't need many keras or anything, because right now we are going to take that. We are going to take the load these. Well, we are not even going to load these models. We already loaded the model before and saved the result. So we are going to only work with data, this one, LGBM segmented image, deep learning segmented image, VGG19 unit segmented image. We're going to load all of these. In addition to that, we are going to load the test masks. So we're going to compare the test masks, which is the ground truth, against all these three. That's exactly what I'm trying to do in this file right here, which means let's go ahead and first load the test mask stack. Okay, and this is again stack of 50 images, each 768 by 768. And I also loaded the image so we can just plot them all at the same time. You don't need the images at this point. Okay, now let's go ahead and load the LGBM segmented, deep learning segmented, VGG19 segmented. Let us do this. And now you should have all of these images, and now all we need to do is just calculate IOU. How do you calculate IOU? You have ground truth and you have segmented data. So you have everything you need to calculate the intersection over union. So let us do that for all of these and print them out and see which one works the best. So, okay, so there you go. Let us run these one more time because we had too many print statements over there. So the IOU for feature engineering, 89%. This is our LGBM. IOU for unit from scratch without any pre-trained weights, about 85%. Not bad. Again, deep learning is not that bad with this much data. VGG19 with pre-trained weights is not that much better compared to unit from scratch, like 86%. So as you can clearly see, when it comes to intersection over union, my feature engineering approach is definitely the winner. I got 89% accuracy. In fact, if I assigned 80% of my training data for training and 20% or even 90 to 10%, I may bump this up a little bit. It's interesting to see exactly how that works out, but 89%, obviously much better than these two. Now let's look at the class 2. Remember, that is the tough one to segment. What is the IOU value for my class 2? So let us print that out. And there you can see I got almost 70% intersection over union. Again, these values are all for the entire 50 images. All 50 images got segmented, and we are comparing against the ground truth. Okay, so I got about 70% right there, 63%, 64% for VGG19. So definitely using pre-trained weights helped, but not by a lot. And this is the case. Most people think that, oh, you use pre-trained weights, so your results must be more accurate. No, you'll get to the result faster if you use pre-trained weights. They may not necessarily be any better. Okay, so in this again example, you can see our standard feature engineering approach worked very well. And now let's go ahead and what am I doing here? Just print out some of the results so we have a good visual understanding of what works best. So let's go to plots and expand this side. If I can find the, yeah, there you go. And now you can see this is my test image. That's the testing label, the ground truth, and this is the feature engineering result. So if you look between these two, they look identical. Every little spot I see here, every little thing I see here is segmented right there. And they all look very good, actually. Even these two look pretty good if you pay close attention. The real thing that you need to pay attention to is this dark region. You see this area? I can see that right there. It's a bit skinny here. I don't have the connection right there. It doesn't even do a great job right here. I mean, you see it doesn't have the same shape right here. Even this region, if you look at this small diamond looking region right there, that looks very good. This region looks very good here, almost identical. But that same region, if you look here, that's not that good. Same with this area, that's not that good. Again, if these type of minor phases that are tough to, minor regions that are tough to segment are important to you, I'm pretty sure they are important. Otherwise, why would you be doing this exercise? Then you can clearly see without a lot of training data, you can get decent results with your feature engineering result. And more importantly, with this approach, you can just work with partial labels. You don't have to label this every corner of every image. The best approach I usually follow is just pick 10 images that represent the volume that I'm trying to segment, and then paint a few areas in each of these images to give enough pixel representation from these different images, and just use those for my traditional segmentation. And please watch one of the earlier videos. Just search for traditional segmentation or random forest based segmentation or feature engineering in my channel, and you'll find many videos on this traditional approach. I absolutely love that, unless I have a very complicated segmentation challenge. And for that, if I have enough training data, then I'll look into deep learning. So I hope you found this to be a good exercise. I know I went through things a bit fast. Maybe some of you think that I explained things way too much in detail. Why don't you just get to the point? I'm pretty sure you're my regular subscriber, so you watched all my previous videos. But I think you found this to be educational, enlightening to some extent. So please go ahead and hit the like button if you like the video, and don't forget to subscribe to this channel, guys. Thank you.